Great. So now that we've built our first circuit, why don't we dive in a little bit to more of the physics and understand what's actually going on by using the water flow analogy.
Great. So our goal here is to teach you a few fundamentals about why we draw circuits using these schematics, what they mean, and a couple of elementary rules that sort of govern analysis of these circuits. So on the left, you've got the circuit we just built. It has the same three components: the battery, the resistor, the LED, and of course the wires that hold it all together. On the right side, we've got this really weird contraption. Now this contraption is resting on the ground, and it's got these blue arrows which represent water flow. So water is flowing through some pipes. And notice also that some parts of it are at different heights, right? So where that little guy is with a lever, it's sort of at a higher elevation than the spinning wheel, for example.
So Michelle, what does the water flow represent? What does it mean on our circuit?
Oh, good question. Okay, so in the contraption, water flow is exactly that. It's just water flowing through a closed circuit of pipes. What we're trying to represent is what's going on with the electrons in the circuit. Historically, we pretend that it's positive charge that's moving around the circuit. And so you get positive currents associated with these positive charges. And that's what you'll see in the drawings in the subsequent slides of this video. Is you'll see these blue arrows that represent what would be positive charge moving around the circuit, analogous to the water flow analogy.
And I hear this is a convention that Ben Franklin came up with many years ago.
Yeah, it's true. Ben Franklin sort of set us down the wrong path, in part because it wasn't appreciated that in metallic conductors, it's electrons that actually move around. And so what's actually happening in the circuits physically is that negatively charged electrons, which are loosely associated with the metal atoms, are the actual things that get pushed down the wires. And so really what you have to think of is what's physically happening is there are negative electrons going in the direction opposite to those blue arrows we're labeling in the circuit. But for the purposes of circuit analysis, we continue to maintain this fiction in a sense that it's positive charge that's moving. So as long as you keep that in mind, and I'll label both essentially for this first video so you can see what's physically going on and also our current labels, you should be fine. So, well, what do you think this little guy is doing, and how does that relate to our circuit?
Well, it looks like this little guy is operating a water pump. So he's moving it up and down, and he's spending work to move water from the lower elevation up to the very top of this pipe. And that's analogous to what's happening in our circuit. Our battery is moving electrons from a high potential to a low potential. And this means that positive current is moving from a low potential to a high potential.
Oh, so I see. So you can kind of think of the potential in the battery, a change in potential is almost like a change in height against gravity, like a change in potential energy. You're adding energy to the electrons. And in the case of the water analogy, then the water can flow downhill. In the case of the electrons can now flow around the circuit through the resistor and the LED.
Exactly, and as they fall down, what exactly is happening with that water wheel?
Okay, so the water wheel is kind of funny, but it's a good way to explain the LED. So you see that when the water flows downhill, it's moving down that diagonal pipe and it hits the water wheel. It does work to move the water wheel, okay? So the water did some work, turned into kinetic energy of the spinning water wheel. In a similar way in the LED, electrons flowing through the circuit go through the LED, and the energy in the electron is transduced. And in this case, what happens is light is emitted. Photons are emitted with a certain energy, okay? And that's pretty much, it's a reasonable analogy for thinking about this happens. The main thing to keep in mind is at no time did water leave that closed system of pipes to make the wheel spin, right? Same thing with this. So electrons continue to flow all around the circuit, and all that's happening is they're dumping energy through the physics that go on in the diode, and photons are released with some of that energy.
I see. So they're still in the wire. They haven't gone anywhere. They've just lost some of their energy as they're falling down the potential.
Yeah, that's right. Okay, but now to finish this off, what's with that poor engineer? She seems like she's holding on to dear life with those little orange ropes. What the heck is that all about?
She's actually got complete and total control over the situation. What she's doing is you might imagine if you take a pipe and you can adjust the diameter of it. So notice she's holding ropes and she's tightening the pipe right in that center, in that section. And what she's doing is she's reducing the diameter of the pipe, which makes it more difficult for water to flow through.
Wait, so that must be like our resistor.
Exactly. What our resistor does is it constricts the flow of electrons through the circuit.
Okay. So that seems a little weird maybe. Maybe why would we use something that makes things inefficient? But we'll get back to that in the next video when we talk all about resistors. But I have a thought while staring at this. So if I had this system of pipes, I could come in and like put a little T-junction somewhere and sort of make water flow down a new branch, right? And I know for a fact that the amount of water coming into my T-junction better equal the total amount of water going down the other two branches. Is that true for electrons too?
Absolutely. If you, just like adding a pipe, you can add a wire to your circuit, and if electrons are flowing from a higher potential to a lower potential, and you put a branch of two wires and give the electrons two directions to go in, the amount of charge flowing into the junction must equal the amount of charge flowing out.
Okay, and this is called Kirchhoff's current law in electrical circuits. Now I want to dive in into a little more detail about both voltage and current right before we wrap up. So what I want to do is give you something a bit more quantitative. If we know that there's charge moving through this circuit. We know that because electrons themselves are charged. And we also know that the battery has something we've called potential. And we've also mentioned something about energy, right? The battery is adding energy to the electron. So I want to put those three concepts together. So first off, charge is measured in coulombs. That's the unit. But coulombs are a ridiculously large unit. So do you know off the top of your head how many coulombs a single electron has?
Actually, I do, and we'll put it up on the screen, but it's 1.6 times 10 to the minus 19 coulombs.
That's a really tiny.
For one electron.
That's a really tiny amount of charge. Okay, so now armed with that idea, right, that each electron that's zipping around this wire has about that much charge, we can give you a formula that kind of relates energy, charge, and potential or voltage. Okay, so we'll be using the term potential and voltage interchangeably. And so the way to think about what a battery is doing and how it interplays with energy is that the energy that's required for a battery to take a single electron and raise it up by a potential of, say, maybe 9 volts. Like the battery we were just using is that potential multiplied by the total charge. E equals V times Q. So I have a 9-volt battery, and I have a single electron. I would multiply 9 volts by 1.6 times 10 to the minus 19 coulombs. That would tell me how much energy I'd have to put in to charge up that electron by that much. It's kind of like asking how much energy that little guy have to do to move water, 1 liter of water up a meter or something like that. That's kind of the same idea. Of course, the formulas are different.
I see. So so in our water analogy, that poor man has to pump even more energy if we make the pipe higher and higher and higher.
Right. So for the same amount of charge, if you were going to go up a higher potential, say 9 volts, 12 volts instead of 9 volts, you'd need more energy. What about current? So we hear the term current. What are the units of current?
Yeah, the unit of current is actually coulombs per second. It's the amount of charge that flows through your wire in a given amount of time.
Perfect. And for those of you that have a little bit more math, there's a nice differential way to express that. If you know a formula for Q, the charge, then the current would be the derivative of charge with respect to time, or dq dt. So I equals q dt. Great. Now I have a sense that there's one last bit that the water analogy can teach us, which is that if I start out on the ground just below that little guy, and I follow the trajectory of the pipe. So I start on the ground and I go up the pipe, and then I walk down the pipe through the wheel, and then come back to the place I started. I end up at the same elevation, right? Does that make sense? I started at a certain height, and if I go through one whole closed circuit, I'll end up at the same height.
Yeah, I think that makes sense if the circuit is completely closed.
Okay, so do you think that holds for the circuit?
Absolutely does. And I would imagine that the same law applies for voltages across the circuit.
It does, and that's called Kirchhoff's voltage law, or KVL. And basically what that says is the sum of the voltages that you encounter as you go around a closed circuit end up equaling to 0. That's the same thing as saying the total sum of the elevation changes if I start somewhere and go around a closed circuit equals 0.
That sounds fascinating. Why don't we check if this law actually holds with our circuit?
That's a good idea. So I think we should quickly try KCL and KVL and introduce the MIDAC and wrap up.